A single logic error deep inside a modern microprocessor can cost a manufacturer upwards of $1 billion to fix. We see the scale of this financial damage in historical failures like the Intel FDIV bug or the Spectre vulnerability. The density of logic gates in hardware, like these vintage Intel Pentium chips, means a single miscalculation cascades into a global failure. To prevent those cascading errors, engineers must verify cache coherency and memory controllers with absolute mathematical certainty. Currently, that verification process is manual. Engineers write out mathematical invariants by hand. The work is slow, highly susceptible to human error, and expensive. The development cycle for secure hardware is currently bottlenecked by the manual throughput of engineers writing and verifying these mathematical proofs. This is where Lean 4 comes in. Lean is a strict formal logic language designed to compile mathematical invariants and verify their syntax with zero ambiguity. Most artificial intelligence models fail when trying to write Lean 4 natively because the language's syntactic rules are uncompromising. Standard large language models operate on probability. They guess the next most likely token. Lean 4 requires rigorous, step-by-step mathematical verification, leaving no room for educated guesses. Before trusting an automated system with complex hardware logic, we tested on combinatorial game theory. These games use discrete, finite states, allowing us to safely map and stress-test the model's logic. The specific testbed we use is the game Octal 0.07, widely known as Treblecross, which we map mathematically through its sequence of Grundy numbers. To solve the manual bottleneck, we built Octal 007. It is an automated code generation pipeline running entirely on a single AMD Instinct MI300X node. Scaling these verification efforts requires moving from manual theorem writing to a specialized Neuro symbolic pipeline designed for autonomous discovery. Current state-of-the-art AI theorem systems like Lean Dojo operate as premise retrievers. They require a human engineer to define and input the finished hypothesis before the system can even attempt a proof. Octal 007 shifts this process towards an agentic discoverer model. This system autonomously scans raw sequence data for patterns before initiating any translation. This diagram outlines the structural difference. The left retriever's flow stops, waiting for human input. The right discoverer operates in a continuous, closed loop. The core of this neuro-symbolic approach pairs a deterministic mathematical search directly with a neuro-language translator. Generalized LLMs cannot verify hardware autonomously. They must be anchored by a rigid mathematical search mechanism to provide verifiable data. The first stage of the pipeline relies on a game data generator. It computes and outputs thousands of raw sequence data points for Treblecross. To proceed, the system must locate repeating periodic invariants buried within those chaotic Grundy numbers. This illustrates the sliding window period detector in action, a purely deterministic mathematical search. As the window scans the data string, it accurately isolates candidate periodic patterns. For Treblecross, the detector identifies exact coordinates, pinpointing a period of 34 and an offset of 52. However, these raw integers are useless to a formal logic compiler without an accurate translation. Identifying these mathematical anomalies is the first step. The pipeline must then formalize that raw data into a valid machine-readable syntax. For the translation phase, the pipeline utilizes the Qwen2.5 Coder 32B model, acting as a specialized neural translator. Running full parameter fine-tuning on a 32 billion parameter model presents a massive computational barrier for standard local systems. We resolve this barrier by executing the entire training pipeline natively on a single AMD MI300X. The MI300X features 192 gigabytes of HBM3 memory. This allows the system to process massive dataset batches locally, eliminating the latency of distributing the workload across multiple nodes. When teaching a model specific tasks, you risk catastrophic forgetting, where the AI overwrites its foundational logic to accommodate new data. This plots our dual-stage fine-tuning strategy. The first curve tracks stage 1, dropping as we feed the model synthetic examples to teach pure Lean 4 grammar. The graph then transitions to stage 2, stabilizing as the model specializes on Treblecross invariants using domain-specific real examples. Combining high-memory hardware architecture with dual-stage training democratizes enterprise-grade formal verification, bringing it directly to the single-node level. With the model fine-tuned, the pipeline enters its final execution phase. The raw invariant coordinates route directly into the LLM for inference. During this step, we tightly constrain the inference parameters. Looking at the execution terminal, the temperature setting is locked at absolute zero. Operating at zero temperature guarantees that the outputs are entirely deterministic and repeatable, which is a requirement for formal mathematical proofs. The resulting conjecture is then piped into the Lean-4 compiler, operating inside an isolated Docker container. The compiler parses the generated code and outputs a verified stamp, confirming structural and typological correctness. This zero-touch compilation represents the first open-source bridge connecting raw sequence data directly to a formally verified conjecture. We must be exact about the system's current limitations. The Lean-4 compiler verifies syntax and type correctness, but it does not yet evaluate the semantic truth of the conjecture itself. Additionally, the sliding window detector was kept intentionally basic. Its purpose is to prove that the Neuro symbolic architecture functions under these specific conditions. Future deployments of this architecture could scale to 70 billion parameter models, built to tackle full-scale enterprise hardware protocol verification. Octal 007 serves as the foundational blueprint. It proves that chaotic sequence data can be autonomously mapped, translated, and formally verified natively on a single GPU.